Hi, everyone. Let's talk about how do you detect a black hole? By the name black holes, these things are very difficult to observe. They do not emit their own light. They do not give off electromagnetic radiation of their own. You cannot see these things. So, how in the world can we detect them? And over the last 30 years or so, science is very certain that they exist. Well, how can we be so certain? What are we using to know that black holes exist? So, we're going to talk about some of the methods that have been used. One way that astronomers have found black holes is by looking at very hot accretion disks. Accretion disks are these disks of material that are rotating around, orbiting, and falling into or towards a large gravitational body. Our solar system began with our sun and the material orbiting it as an accretion disk. But around a black hole, we are finding accretion disks. This is this combination of matter and gases that are crazy hot in the nature of 10 million degrees Kelvin. Now, if you recall, a Kelvin degree is the same size degree as a Celsius degree. It just 0 Kelvin starts at absolute zero. To give you an idea, the face of our sun has a temperature of about 5,000 Kelvin. So to have a disk surrounding nothing, something we cannot see, that is 10 million Kelvin, means that it is crazy hot, very, very, very hot. So that means it has a lot of kinetic energy, it has a lot of speed, and something has got to be giving it all that speed and rotational energy. And what is that energetic that can accelerate it to that great extent? Well, that can be a black hole. How can we see these high energy hot objects? Well, we can see them in infrared, and the James Webb Telescope, which is designed to be very, very good in the infrared, is going to be a magnificent tool to assist us in finding these hot accretion disks to indicate the presence of black holes. One of the other things we found, ways we can detect a black hole, is by watching a star that is orbiting with an invisible partner. As we've discussed, about 50% of stars are not solo in the universe. They have a binary partner. And very often a star is seen to orbit nothing. It is rotating or going in a dance out there in space, and there is nothing out there that it is spinning around. If there is an invisible gravitational something and these two objects are orbiting each other, what is this mysterious other out there? Well, if we can't see it, very good odds it is a black hole. I'm going to ask you at the completion of this to watch this quick little 15-second video. It is an older video, but I wanted something that is short in time that will give you a piece of the picture. Andrea Ghez and her team have been working for decades at plotting the path of stars in the center of our Milky Way galaxy. And with a lot of detail, they have slowly gathered a movie of what the stars are doing in our center of our Milky Way. And they are orbiting something we cannot see. And that is the black hole, the supermassive black hole in the middle of the Milky Way. Another way we can detect black holes is by X-ray emissions. Any X-ray, whether you go to the doctor for dental X-rays or you have a broken foot and you need your foot X-rayed, all X-rays are produced when a charged particle is accelerated very, very quickly. And when you get an accelerated charged particle, and especially if it slams into something, one of the products very often is an X-ray. Well, it takes a lot of energy. X-rays in the electromagnetic spectrum are very high energy types of electromagnetic light or energy. So these are big energetic things. You have to put a lot of energy out to get an X-ray out. Well, the Chandra X-ray telescope was launched specifically to look at space in the X-ray portion of the spectrum. And in the optical portion of the spectrum, you might see something that looks like that, but in the X-ray portion of the spectrum, you go, boy, howdy, that is loaded with X-rays. Well, how does a black hole produce X-rays? Well, it doesn't. But as matter is plummeting in through its event horizon and falling into that black hole, it is rapidly accelerated, and accelerated matter makes X-rays. And as things are falling, matter is falling into that black hole, it is releasing massive amounts of energy as it's going, no, and falling into that event horizon. And that is one way we can detect those black holes. Gravitational lensing. Things that have a lot of gravity, huge gravitational forces around them, bend light. This is a product of Einstein's general theory of relativity. And we'll talk more about this gravitational lensing when we get to our discussions about dark matter. But this is another way we can find, especially those super massive black holes in the centers of galaxies. And these things are so big that they actually bend light around them. They will distort any light that passes nearby. So let's talk about what a gravitational lensing is going to look like. Let's say this is you or I on planet Earth. This is one of our telescopes up orbiting the Earth. And we're trying to take a picture of a galaxy way the heck over here. Between us and our target galaxy up here that we're looking at, there is something very, very large. Maybe it is a spiral galaxy, and in the middle of it might be a huge, massive, supermassive black hole. Well, as we send our telescopes in this direction, the light from this galaxy, instead of going straight, as it goes near this supermassive galaxy or supermassive black hole, what happens is the light, instead of going straight, is bent because of that large gravitational force. Now remember, this is how Eddington proved the existence of that general relativity worked, because of gravitational lensing of light. Well, we can use that, because if something is massive enough to really bend light a lot, we can use the quantity of bending, how much is the light bent, to help us calculate the mass that we are looking at. And so it is a cool technique for detecting these supermassive black holes. When an astronomer is looking at this far distant objects and it sees what is called an Einstein ring. An Einstein ring is going to look something like this. So the object in the middle is the foreground object. This is the thing that we see in the front. So this would correspond to what we see here. And what looks like a ring kind of smeared around the object, this ring that's smeared around it, what that is the object behind, and that behind object has been smeared all the way around it due to gravitational lensing, and that is an Einstein ring. Another way of detecting black holes is with something called gamma ray bursts. Gamma ray bursts are the most powerful explosions in the universe today. Great quiz question. What are the most powerful explosions in the universe today? Gamma ray bursts. They're very, very short. They last about 20 seconds on average. Each one is very unique and very different. No two gamma ray bursts are exactly the same. And if you remember our discussion of the electromagnetic spectrum, on the high energy light end, you've got visible light, the good old Roy G. Biv, ultraviolet, X-ray, gamma is way down here, the highest energy, very, very high energy end of these. And we see these gamma ray bursts all over the universe. Where are they coming from? What is their cause? Well, back in 2004, the Swift telescope was launched, and its purpose was to look for gamma ray bursts. Originally, we thought they were quite rare. Now we find at least one per day, and it's only in the direction that the Swift telescope happens to be looking. Most of these, fortunately, are coming from billions of miles away, well outside the Milky Way galaxy. What we think the gamma ray bursts are produced by is the birth of a black hole. So if we look at that, there is at least that we are able to detect one new black hole that is being born every day. That is a lot of black holes. So something that 30 years ago was kind of theoretical, now they are born all the time, constantly all over the universe that we can detect. So they're really, really common out there. So how does a gamma ray burst get produced? Well, in a stellar mass black hole, normal life cycle of a star, you have a huge star at the end of its life, and it starts to implode when it doesn't have enough heat to keep that big red giant star expanded. So as it starts to implode, its magnetic field also starts to get smaller. And as it gets smaller, this huge, massive implosion is going to lead to it becoming a black hole. But it still has a residual magnetic field around it. Whoops, a residual magnetic field around it. We think that this high energy radiation comes spewing out of the poles of the magnetic field, in the same way that the Earth's magnetic field, the north and south pole, is where the auroras can be formed. And we think these tops and bottoms of that magnetic field, that's where we get those gamma ray bursts. Very short period of time. Remember, about 20 seconds is all of the time that these last during that implosion at the birth moments of a black hole. Other times, we think gamma ray bursts can be produced from two neutron stars colliding to form a black hole. That's a pretty exciting explosion out there, or collision, or neutron stars colliding with a black hole. So they're pretty exciting things, these gamma ray bursts. They, just like pulsars, we believe there is a lighthouse effect. So if we are looking at them from over here and the burst is aimed that way, we're not going to see it. So at one per day, we're only seeing the gamma ray bursts that are aimed at us. The ones that are aimed away from us or down towards, outside the solar system, we're not going to see. Again, I'm going to ask you to watch a short video on gamma ray bursts. They're pretty cool things, and I hope you enjoy it. All right, talk to you soon. Bye-bye.